Welcome to Brain Vision.
In this example, we have a massless piston here that's attached to a spring in this closed-off cylinder, and it's got gas sitting under it, and the pressure of the gas makes it so the piston spring system here is displaced from its equilibrium position by a distance x naught. Now, what we're going to do is we're going to heat this gas up so that it displaces to a distance of x final, which is 0.1 meters instead of 0.8 or 0.08. And what we want to know is, what does the final temperature have to be in order for us to have that displacement? So let's see if we can figure that out. So I've written out all our knowns and unknowns here. So we know like the initial temperature, volume, the cross-sectional area of our piston. But other than that, we're kind of in the dark. So let's see what we can do. So the first thing we should always remember is that we are dealing with an ideal gas here. So we should remember the ideal gas law, PV equals nRT. And what we're trying to do is find our final temperature. So imagine these are all final amounts here. And we want to solve for T final. So we could divide both sides by nR. And we would have that T final is equal to P final times V final over nR. Okay, so what do we need to calculate this? Well, we don't have P final, and we don't have V final. So let's see if we can break those down. Well, for V final, we know what the initial volume is here, and we know that that corresponds just to this area under the, or this volume under the piston here, right? In this region. So that's V naught. And after it stretches up to X final, we just add a little bit more volume. And the little bit of volume we add is going to be shaped like a little cylinder, something like this. So before, we had a distance from equilibrium up to here, which was X naught. And then this distance up to here will be X final. So the volume of this little cylinder that we'll be adding to our total volume is going to be the difference between X final and X naught times the area or the base of that cylinder, right? The base, or the circular base of a cylinder times its height, will give you the volume. So if that's true, then our final volume is, like I said before, our initial volume plus that little extra bit we added from moving up, which is shaped like a cylinder. And that has dimensions of A times X final minus X initial, or X naught. Okay. So let's see if we know everything we need to calculate that. We have X final and we have X initial. We have the area and we have the initial volume. So we can just go ahead and calculate that right away. And then we know we have the volume for our calculation in the future. So if we plug in those values, we'll get 6.5 times 10 to the minus 4. Okay, I'm going to move this equation down just a little bit so we have some more room. All right, so now we've dealt with our final volume. So what about the final pressure? Well, since this system is at equilibrium, we know that the pressure acting upwards on this mass here is equal to the force resisting it from the spring. So how could we write that with Newton's second law? So Newton's second would say that the sum of all forces is equal to ma, but since we're at equilibrium, the sum of all forces is really just zero, and we only have two forces. We have the force up from the gas and the force down from the spring. And if you recall from mechanics, the force from a spring is going to be from Hooke's law, which is a constant k times the displacement of the spring, x. So in our case, that would be x final in the final scenario. So if we were to rearrange this, just add this kx to the other side, we would have, and actually I'm going to name this just F final for the force in the final situation. We would have something like F final is equal to KXF. Now imagine we did the exact same thing for the initial scenario. We'd have a very similar equation, right? It'd be F naught equals K X naught. And the reason I write down both of these equations is because we've introduced this unknown spring constant here, and I don't want to keep it around because we don't know what its value is. So we're going to need a couple equations to substitute it out. Now also, you'll notice these are in terms of forces here, but when we deal with gases, we generally want to deal in pressures, right? So imagine if I divided both sides of these equations by A, the area, we would have the force over the area equals KXF over the area, or a force over an area is just our pressure. So this would be P final. And similarly, we could do the exact same thing for the other equation. So we could have P naught is equal to Kx naught over A. All right. So now we can eliminate K from both of these equations. If we solve for K in both of them, we'll have, let's see, we'll multiply by A over X naught for this one here on both sides. And we'll end up with A times P naught over X naught is equal to K. And for the other one, we'll have something very similar. A times P final over X final is equal to K. So we can set these equal to each other since they're both equal to K. It's the same spring constant for both scenarios. And we'll have A P naught over X naught equals A P final over X final. So our A's cancel out because those are the same for both situations. And we have this nice little relationship between the initial and final pressure and the initial and final displacements. So this is going to come in handy because we know what our initial pressure is. We know what our initial displacement is. We know what our final displacement is. So we can solve for P final. So if I multiply both sides by X final here, I'll isolate P final. And I'll have P final is P naught times X final over X naught. So now I can go ahead and solve for P final, or I can just put this into my equation for the ideal gas law. Either way. So let's just go ahead and put it into our equation. So we have T final is PF VF over NR. Let's just rewrite that. PF VF over NR. And I am substituting out this PF for our new PF. So this will be P naught times X final over X naught times VF over NR. All right. So all of this stuff we have readily available. And actually, we still have a little bit of a mystery on our hands because we don't know what the initial pressure is, and we don't know what the number of moles is. But no worries, because there is a solution. What we're going to do here is just use the ideal gas law for the initial setup, which is going to be P naught V naught equals nRT naught. And we can just substitute in for the P naught over N here. So if I rearrange this equation to get P naught over N, so divide both sides by N and divide both sides by V naught, I will get R T naught over V naught. So you can see this P naught over N in here is what I'm going to substitute out. And if I do that, I will have R T naught over V naught, X final over X naught times V final over R. So our R's cancel out, and we're just left with, let's see if we can write it a little cleaner. T final equals X final over X naught times T naught V final over V naught. Something like that. Okay. So now all of these values we have. We have the initial temperature, volume, final volume we calculated a moment ago, and these two displacements. So if we plug all of those in, we're going to get that the final temperature is 370 degrees Kelvin. So this was a little roundabout because we had to do a lot of substitutions and an extra one there at the end. And probably a cleaner place to start would have been by taking the ideal gas law, PV equals nRT, and asking ourselves what stays constant between these initial and final situations here. And we know that the pressure, volume, and temperature actually all change, but what doesn't change between them is N times R. So PV over T equals NR would be a constant during this entire process. So what that means is that we could have written something like PV over T initial equals P final V final over T. And then have gone from there, and that might have saved us a little bit of trouble. But there you have it. We determined the final temperature of this piston spring system after heating the system such that the displacement went from 0.08 meters to 0.1 meters.